My name is Stafford. I'll be reporting on the thermocouple time constant experiment. Quick overview of the experiment. A thermocouple that is attached to some data acquisition software was submerged into some ice water. It was allowed to reach a steady state temperature of the water. It was then removed and quickly dried and allowed to reach the steady state temperature of the room, and all the data was saved. The thermocouple used was a type K. It is made of two dissimilar metallic wires that are joined together to form a junction. This junction generates a small current in response to a change in temperature, and when handling the thermocouple, it's important that it only touch the water that it was measuring and not the beaker, and it had to be dried when it was removed. The goals of the experiment are to observe the response of the thermocouple to changes in temperature, properly acquire all relevant data to calculate the time constant of the thermocouple, graph and curve fit the results, and to practice lab safety in doing so. As you can see, the results of the experiment in the beginning, the time for the data acquisition probably started late. You can see 1 point up at about room temperature, and then it sharply drops down to nearly freezing temperatures. Whenever it was removed, temperature started to rise. It was plot shown separately, insertion and removal. In order to find the time constant, I used the lump capacitance method. It assumed that the temperature of the water was constant throughout and that the heat transfer was done by convection only. And energy balance was done to get this, which is the energy stored equal to the energy in plus the energy generated minus the energy out. There was no energy going into the thermocouple and no energy generated due to the constant temperature. After integrating, rearranging, and substituting the energy balance, the time constant could be solved for in terms of the temperatures and time gained during the experiment. Since the ambient and initial temperatures were already known, and the time constant represents the time that it takes for the thermocouple to respond to the changes in temperature. The results were normalized with the changes, or the transient temperature minus the ambient temperature of either the water or air, depending on which it was, over the initial temperature minus the ambient temperature. The results normalized shown here with the slope equations. And in order to get this, the time constant, the negative log of the normalized temperature was plotted against time, and the slope of this line is the time constant. So for the insertion, the slope was 33, and for removal, the slope was 144.75. Now, the removal time constant was over 4 times larger than the insertion time constant, and since the time constant equation, everything in the numerator, so the density, volume, specific heat, are all the thermocouple, those are constant, and the area on the bottom is also constant of the thermocouple. The only thing that changes is the convective heat transfer coefficient. So in insertion, the heat transfer coefficient was 500 to 10,000. And for extraction, it was contacting air where the heat transfer coefficient was 10 to 100. This explains the big difference in the time constant, and also why it's important for the thermocouple to be dried when it was removed. The time constant can be manipulated or changed by changing the fluid that the thermocouple is exposed to or the material the thermocouple is made out of. Now, what if we've done this experiment with boiling water? So the temperature difference between freezing water and room temperature is much smaller than between boiling and room temperature. The difference in temperature for nearly freezing water would be about 25 degrees Celsius, and for boiling it would be somewhere around 75. Because of this, it would make sense that it would take longer for the thermocouple to adjust, making the slope and time constants much larger. Are there any questions?